In this video, we're going to be analyzing two problems with a bunch of forces acting on them, and then we're going to be solving for the acceleration. The first one, we're going to be using all numerical values to talk about the concepts and problem-solving process. In the second one, we're going to solve it in terms of all the variables and how those concepts and all that algebra works. So for our first one, we have an applied force of 80 newtons directed in the downward left position or direction. And the first thing you always want to do is start off with your free body diagram and draw your forces. I'm going to draw them right on my box though. So we of course have Fg pulling straight down from the earth. We have a normal force pushing up from the ground perpendicular to the surface, supporting it. We have this applied force already, so I'll just kind of leave that one there. And then we have a mu sub k, so we definitely have some friction opposing the slide in this direction. All right, now anything that doesn't fit perfectly along your vertical or horizontal axis, you want to make sure you put some components with it. So my applied force is obviously on an angle. It's not vertical or horizontal. It's a little bit of both. We have a vertical and horizontal component to this one, which I'll call FAX, and then we'll call this one FAY. Okay, now that's not actually part of my forces, those are just pieces of my FA. Now what I want to do is analyze each of the axes separately. So I'm going to take a look at the sum of the forces in the x direction, which is also known as the F net x. Now in the x direction, I have something called an FA, just the x component pushing it to the left. I'll call that my positive, and then I'll say my force of kinetic friction is opposing the slide. Whoops, I'll put that F over there. And we know that our net force is always equal to m times a. Secondly, we have the sum of forces in the y direction. And this one, if I'm taking a look at it, I have two of them going down, my FAY and my FG, and then I have my FN going up. So I normally say everything up is positive, everything down is negative. So FN is my positive minus my FG minus my FAY. Okay, and that one is going to equal m times a2, but I know that's going to be equal to 0 newtons because in this particular scenario there is no movement or acceleration in the vertical direction, so I'll just call that 0. All right, now my ultimate goal is to find this acceleration right over here. So let's go ahead and plug in some numbers. Now I have FAX that I want to plug in, and I want to plug in FFK. If I want FFK, I know that I want mu times the normal force there. So I already have mu in my givens, it's 0.1, and the only way to find normal force is to find it right over here. So I know I want to solve for that at some point. My FAX is going to be pretty easy because I have the hypotenuse of my triangle, which is 80, and I have an angle of 20 degrees to work with, so I'm feeling pretty good about that. So if I want the vertical component, I'm going to use sine because it's opposite of my theta. So sine of 20 degrees equals the opposite end, the FAY, over the hypotenuse, where the hypotenuse is 80. Okay, so I'm basically going to multiply 80 on both sides. 80 times sine of 20 is going to give me my FAY, which is 27.36 newtons if I round it to the hundredths place. Similarly, for my x, I want the adjacent side to my theta. That one I'm going to use cosine of 20 degrees, and that's equal to my FAX over the hypotenuse as well. I know the hypotenuse is that 80 Newton force that they originally gave me. Same thing, multiply both sides by 80. 80 times cosine of 20 is going to give me 75.18 newtons. All right, so that's a bunch of useful stuff that I'm definitely going to need. This force right over here and this one over here. All right, so now I'm ready to go. Let's go ahead and start plugging in some more numbers. We have 75.18 over here, and then we have 27.36 over here. Okay, I know my FG, we can always get that by mg, which is mass times 9.8. That one I can do in my head because the mass is 10, and 10 times 9.8 is just 98. So that one worked out pretty nicely for me there. And now it looks like I'm in pretty good shape because I have everything except my Fn. So I'm going to solve for my Fn by adding 98 and 27.36 to the other side. And then I got 125.36 newtons. Okay, now remember, Fn isn't equivalent to Fg in all cases if there's some other vertical forces. If it was just sitting at rest, then our Fn would be equal to Fg, but since I have a little downward force shoving it into the ground along with the Fg, the Fn has to be able to counteract both of those, so that 125.36 is obviously bigger than my 98 from the Fg. All right, now going up to my top part, I have mu k, which is 0.1, the coefficient of kinetic friction, times my normal force. And that's going to allow me to get my net force. All right, so let's scoot this over a little bit. And I have my FAX minus the product of my 0.1 times 125.36. And that gives me a net force of 62.644 newtons. Okay, that net force, I can go ahead and set that equal to MA. And my M was 10 kilograms, and got that and the other side, so I'm going to go ahead and just divide both sides by 10. And then now we have a final A value of, I'll round it to 6.26 meters per second squared. All right, so recap. Number one, you for sure want to do your force diagram or your free body diagram. From there, when you do the sum of forces in the x direction and the sum of forces in the y direction, only things that are horizontal go in the sum of forces in the x, only things that are vertical go into this one. So since we have an angled component, you basically close it off into a right triangle, so you have a vertical and horizontal component. And then from there, you place all your forces into a formula. Oftentimes one of them is equal to 0. This one we had a 0 right over here, because we have no motion or acceleration in the vertical direction. So now I'm focusing on my sum of forces in the x direction and looking for everything I need. I found this FAX right over here by doing a little bit of trig, and then I found my mu k times Fn by, well, I already knew my mu sub k, and then my Fn I had to use my sum of forces in the y to get that value. From there, I was able to get to my final setup, which is the net force equals m times a, and then from there some basic algebra, dividing both sides by 10 and getting my final acceleration of 6.26 meters per second squared. Okay, obviously not every question is asking for the acceleration, but you basically fill in as many numbers as you can and then work your way towards the solution. Now for our second problem, we're going to be looking at a scenario where someone is pushing a block up an incline, and we're going to solve for the acceleration in terms of mu sub k, fp, mb, and g. This one is going to be a little bit more complex than the first one, and it's focused more on the concepts and knowing your trig and algebra as well. Alright, so if we go ahead and draw a free body diagram, we have the FG straight down. We have the person pushing it up the ramp, which is known as the force of their push. You could probably call that an FA, an applied force as well too. And then you also have a normal force perpendicular to the ramp. And because it's getting pushed up the ramp, then we're going to have kinetic friction opposing the slide. Now for anything that's on an incline or decline has a unique characteristic, which is it has to be analyzed on two different axes that are tilted. So we have a horizontal and a vertical axis. The horizontal one is now known as the parallel axis, and the vertical one is now known as the perpendicular axis, because all the forces are going to be operating perpendicular or parallel to the surface. So you're basically taking your x-axis and your y-axis and then tilting it to match up what's going on with the ramp. Now the same rules as before. After you draw your free body diagram, we want to make sure all our forces fit along the x and y axis. All my blue vectors finish up my force diagram, but now I have an FG that's actually not fitting along one of my axes. So I want to give it a perpendicular and parallel component, which I'll call FGY and FGX. Okay, now I have everything sitting along my new x and y axes. So for all of my forces that are along the x direction or parallel, whichever one you want to call it, we have the force of the push that is propelling it forward, and then we have the force of kinetic friction that's opposing that slide, and that's equal to m times a as usual. And then we also have the sum of the forces in the y direction, also known as the perpendicular direction for this ramp. We have our Fn going upwards on the ramp, and then we have our Fgy going downwards on the ramp. And that one is going to be equal m times a, but I know that's going to be 0 newtons, so that because there's no motion that is perpendicular to the ramp. Okay, actually I noticed I made a mistake in the first part. We have Fp minus Ffk, and then also I forgot to subtract my Fgx, because that's going down the ramp as well. Alright, so I got all my horizontal forces, all my vertical ones, and now we're ready to go with doing some substitution. So we know we eventually want to solve for the acceleration, so we're going to have to do a little bit of trig and moving stuff around as well. Now, if you want everything in terms of these four things, I want to make sure I'm strategic in working those out so that we have an answer that's in terms of those four unknown variables. So we have Fp, this one's good, we can kind of leave it as is. We have Ffk, which is going to be mu times the normal force, okay? Mu actually works because that's one of our variables that we want in terms of, but Fn, we're going to have to find some way to substitute that out. And then same thing for our Fgx. All right, so now we're thinking we have this right triangle over here, our Fg triangle with an Fgy and Fgx. Now our angle theta over here actually translates over here to being the theta over here. Now if we use that, if we were to use the numbers, again, we're going to use sine and cosine, and Fg as our hypotenuse. So if you look opposite of theta, that's where my Fgx is at. So Fgx ends up being Fg sine theta, which we're going to rewrite as mg sine theta, because we know Fg is mg. And then also similarly in the y direction. Now in the y direction, you can kind of see over here, theta is, or Fgy is adjacent to the theta. So we have Fg times cosine of theta to get that adjacent side, which then ends up being mg cosine theta. All right, so now we like that because it gives us more things in terms of the variables that they gave us. So we can write our Fp as it is, because that's one of the terms they allowed us to use. We can write our Fgx now as mg sine theta. Over here, we still want to keep this ma as it is, and then this side, we want it to be mu times normal force. Okay, here's the thing. we can't use Fn as part of our answer. So we're going to find Fn. We see it right over here in our sum of forces in the y direction. And we do actually know Fgy with our little bit of trig work over here. So Fn minus Fgy equals 0, which would mean Fn equals mg cosine of theta. Okay, we're going to take that and then substitute it in right over there. All right, so let's go ahead and clear out a little bit of room and then do the last bit of rearranging to solve for A. All right, now in green, I made all my substitutions. I got the FP here, the mu sub k with my mg cosine theta that we just talked about, which is my Fn that was equivalent to my Fgy. And then I have my Fgx as mg sine theta. So to solve for A, all I have to do is divide both sides by m. So take this entire thing and then put it over m. So double check. I have everything in terms of Fp. I got that in the beginning. Mu sub k, it's in there once. And then I have my mass and my g. I can put the little subscript for the b next to the m's for just mass of the box. Either way, it's the same thing. All right, so when doing this kind of problem, again, it's pretty similar to what we did with the previous one. You start with your forces and you analyze those vectors to see if it's along your x and y axis. Your x and y axis is typically just completely vertical or completely horizontal. If something's on an incline or decline, then you go parallel and perpendicular, just like the case we're looking at now. Then you analyze any vectors that fall in between those axes. In this case, our FG did fall in between our parallel and perpendicular. In that case, you close off a little right triangle to get a vertical and horizontal component. So that when you do sum of forces in the x and y, you can place all of those vectors in their proper category. From there, you do some trig, some algebra, kind of expanding things out as much as possible. This one we had a specific goal of solving stuff in terms of 4 different variables, so we know we needed to do a little bit of trig before we did some algebra, and we were able to solve for A. So that's the problem-solving method. If you saw both of those two examples, the approach of it was pretty similar. So you have to be pretty methodical about setting up your diagram, your sum of forces in each of the axes, expanding out to different formulas, plugging in numbers, and then hopefully you'll find your solution. So I hope that was helpful to you in mastering the forced problem-solving process. Thanks for watching and listening.